Good morning, Stellar Navigator. We're still bobbing atop the cosmic waves of an alien ocean, but not for long. Today we can sit back and relax, knowing we've done everything we can to prepare for launch, our big day tomorrow. Yeah, big day. Lots of moving parts will be launched tomorrow, and everything needs to happen at precisely the right time, or the ocean will turn into an explorer-flavored crater. Time. Time is of the essence. Time is short. Time won't give you time. Time. Okay, we're not quite done. We need a timer. All right, you clever explorer. Today's hardware task is a piece of interstellar cake. We're simply welcoming back our old friend, the 7-segment display, to our current setup. Yes, that's right. The same one that played a crucial role in lighting our way up from the deep ocean. This won't be anything new to you. Just plug the 7-segment display into the wiring layout from yesterday. Easy, right? With each step, we're getting closer to our grand liftoff. As always, ensure that your connections are firm and correct. Let's get to it. Let's have a small detour to define macros. When you see define in our code, it's essentially a way of creating a shortcut or an alias. We set a keyword equal to a specific value or string of code. This way, instead of having to type out the whole thing every time, we can just use the keyword. It is also useful when we have the same thing written in multiple places, like occasionally pinouts, so we only need to change it once. This makes our code cleaner and easier to understand. It's like having a code name or a shorthand for your favorite lengthy space lingo. All right, on to today's simulation. We'll be adapting the done code from our Day 16 adventures for our 7-segment display. This time, it'll be there to signal the end of our countdown, like a digital pat on the back. If everything goes according to plan, tomorrow we can connect everything up to our thrusters. And then, well, you know the drill, liftoff. We're in the home stretch, Explorer. The stars are within our grasp. Let's ensure this simulation goes off without a hitch, and prepare ourselves for the big show. For today's coding spree, we're going to cook up a function that sends us on a countdown journey. It's going to be an exhilarating watch, I promise. Once we're done, we'll celebrate by lighting up our 7-segment display with the victory chant, done, just like we did back on Day 16. Imagine it like a digital high five. If all goes well, this is precisely where we'll inject the codes for our long-awaited liftoff tomorrow. It's exciting, isn't it? Hold on to that curiosity, Explorer, as you walk through every line of our code in the daily breakdown. As always, I've cached it to your mission resources, so buckle up, it's coding time.
Hello everybody and welcome back to day 23 of the 30 Days Lost in Space Code Explanations. Today we're going to be introducing the 7-segment display in order to have a nice countdown timer for tomorrow's liftoff. Since the 7-segment display is something we have talked about previously in the past, just as a heads up, if you want to learn about a lot of the stuff that's talked about in today's lesson, a lot of the stuff that's referencing the 7-segment display I'm going to glance over, as it was heavily discussed in day, I believe, 16. So take a look there if you're interested in any of refreshers on the 7-segment display. Going down, you'll see we included that library, and down below that we included the library from yesterday so that we can draw our nice fancy little shapes that we all enjoy. In particular, we're going to be using it to draw a spaceship on our OLED display, so that's going to be really cool later on. Down below that, we now have a new concept I'm introducing today, and this is called a macro. Now, I'm sure you've seen before where you can say define, whatever pin to be 5 exactly right here. Here's a good example for the 7-segment display. But you can also use this to create essentially calculations, almost do the exact same thing as functions. Another way you could write this could be int number of minutes with the input for this function of milliseconds. And then you could have return, obviously inside, return milliseconds plus 999 divided by 1000 divided by 60. This could be the exact same thing, but this is a nice shorthand version that does the exact same thing. So anytime we want to calculate the number of minutes, when we know how many milliseconds there are, we can just take this and then pass in the amount that we want here, and it'll do the calculation and return it for us. And the reason we're using the divide here is because obviously that will get us the number of minutes. And then this is another symbol that I don't think we've talked about too much. This is modulus, and modulus gives us the extra after a divide. So let's think about whole numbers for a second so you can understand what modulus is. So let's say you have a person named Sally, and Sally has 3 apples. And let's say she has 2 friends, and if you were to do a divide, she doesn't want any apples. She wants to give all of them to her friends, right? So if you were to divide using this symbol, obviously, you would get exactly 1 and then half. But let's just say you wanted to know the remainder, and you wanted to divide only an even number, so you can't give half an apple. The modulus gives whatever the division is, so each person gets 1, 1, and then the remainder is 1. So each person gets 1, and then you have 1 left over. The remainder of 1, the thing that's left over at the end, is what the modulus equates to. So if we go back to our code, and we want to look at this, the number of seconds is simply going to take the number of minutes, and then how many seconds are left after that, right? And then that's what the modulus gives you. So if you only, if you have still like, 32 seconds out of the minute, well, that's what number of seconds is going to get you, 32 seconds out of the minute. The reason these calculations are going to be really nice later on in the code is that it's going to be able to let us display exactly what we want to on our 7-segment display, which we'll be showing here in just a minute. Obviously, these are the defines for the pins for our TM display. All this was talked about in how the library works, I believe, on day 16. So I'm just going to briefly go over that. And down here, we talked about this yesterday. This is, we need to define our lander display from our library. And wonderfully, we can just use this here. And so instead of calling this every time, we're going to call lander display because that's a lot easier to call than this mumble jumble garbage. Down here, we have the height and width of the lander that we're going to be drawing on our OLED today. And we will be drawing that using the library up here. That gives us all the functions to draw the squares and triangles and all those other stuff. We can say done on the 7-segment display by doing this. Again, explained in day 16, each of the segments, defining each one that's lit up. For D, for O, for N, and for E. Down here, we have the countdown milliseconds in how much time we want it to count down. So if we want to change the countdown, instead of being 5 seconds, which is how this is currently at, to, let's just say we want to make the countdown 30 seconds, we can change that right here, if we so desire. Going down into setup, setup's actually pretty big today. Normally, all we would be doing in setup is saying, here's the pins, here's the pinouts that need to be set, here's whatever. Here, for example, we're setting the brightness of our display because we only really need to do that once. For our 7-segment display, we're clearing it. The lander display, we're just going to initialize it with the OLED. It's just going to set the pinouts, etc. Set the text font, set the reference height text, set the font position to top. So all the text going forward will be rendered from the top down. So instead of it being by calling this function, we're going to allow it so, as I explained yesterday. So as you recall, as we talked about yesterday, you can, if you want to display the text like hello world, and you're on our little OLED display, by setting the position to the top, it's going to start here and render it down like this. But if you didn't have that and you had it set the other way, it would start from here and it would then say HELLO world, like that. But the issue is that obviously, so if you wanted to say it at 0, 0, for example, that's going to be off screen. So by putting it so it renders from the top and just setting that position, that in here in the code, we're going to make it so that it, when you do it, it's going to start from the very top left. Finally, we have probably, I would argue, the most complicated thing that I've had to teach so far, given the code that we've looked at in general. Now, I want you to remember what device we're using. We're using a microcontroller that has a very, very limited amount of memory on it. A limited amount of RAM, so only a certain amount of functionality can be done. Now, let's be real. We've already done quite a few amazing things with the very, very limited processing power that we have available to us. But with that being said, I think we're finally on day 23 and we're just starting to finally hit some limitations. So, as you might know, graphics take a lot to render. A lot of memory to render graphics. There are, however, methods that you can use to reduce the amount of RAM necessary. It does take a little bit more processing time in order to do that, but there are methods to do that. So if you're going to be drawing an image on the screen, in this case, anytime we want to update our screen, we literally have to tell it, put this pixel at this point, put this pixel at this point, put this pixel at this point, essentially. You know, we're saying which ones we want to turn on, we want to say which ones we want to turn off. What we can do is we can get the entire defined, like let's take all this and then blast it to the screen, but that's going to take a lot of memory. So what happens is, first, your code does some calculations, right? It says, okay, I want to display a smiley face on the screen. That's what your functionality is for, let's just say, this theoretical program. Okay, so you could do this in a few different ways. One is you could define, okay, I want to draw this eye first, this eye, and then this is all being saved in memory right now. This is not on the display. And then I want to draw the nose, and then I want to draw the big old smiley face, and this is all in memory, and then I want to push it. Now push the entire thing right now, all of it, all at once, this entire face, all on here. This will all being stored in memory is on here, and eventually goes down to be empty, so this is memory, and now just empty. And then this turns to, obviously, the face. The issue with that is that by doing it that way, you're going to store a lot of extra stuff in memory all at once. So the amount of memory needed to store all that extra volume of stuff in this top left is a lot more. So instead of writing everything that you have in all of the screen all at once, we can save a little bit to memory at a time, and we can send a little bit to the screen at a time. And remember, this is going to happen so quickly that it doesn't really matter at the end of the day, because it's so quick your eyes won't even be able to really see it. Let's start by step one. We're going to draw maybe the top left, or we're going to draw like the very first little bit of the image, right? It's going to be the eye, and then that very first part of the nose, okay? Step two, and then after each step, we're going to push this to the display. So this is now going to have this on the display. We're going to push just this. So this is going to be memory. This is going to be what's actually showing currently on the display. And these four things are going to execute very, very quickly. So you don't have to like think too heavily about it, because it's not like you're going to see these in-between changes, because the computer's processing everything so quickly. So the first way we showed of doing it is by just taking the entire face, loading it into memory, and then pushing the entire thing to display. But by doing it this way, you can use 1/4 of the amount of memory in this theoretical scenario by just putting this into memory, pushing it, this into memory, pushing it, this into memory, pushing it, and this into memory, pushing it, which uses way, way, way less memory to do it that way. And you can divide it up as little as you want or as much as you want. That's entirely up to whoever designs the algorithm to do that. In this case, the algorithm was made by the library, and they use a function to do all of this. It's called first page and next page. And you usually do this in a do-while type structure of a loop. And what it'll do is it'll just call first page, and then it'll say do all this stuff. We're basically going to, what we want to do is we want to essentially, instead of loading parts of a smiley face into memory, we want to load into memory the strings exploration lander, liftoff sequence, and countdown active. And then we want to obviously display a picture of our lander in the very bottom right corner, right as the countdown timer is going to take off. So we're going to be storing bits and pieces of this into memory in a form of a loop to save on, obviously, the limited memory that our controller has. Then we're obviously going to blink the countdown timer on our timer before beginning the countdown. And we're also going to, after all this is completed and all that setup is done, we're going to jump to loop. Time remaining is a static variable, which means it's going to remember the value that it had last time we went through the loop. So this is essentially going to be as effective as a global variable, sort of, kind of in its own roundabout way, but we don't actually have to make it a global variable. Next, we have this static variable called countdown start time, and this is quite literally going to get the start time of when it got to this point in the code. When it calls millis, or is a function built into the Arduino library, and all it does is it checks to see how the time from the very beginning of the execution on your board to the second it hit this line of code. So that what this is going to do is it's going to get the exact moment it hit right here. Next, for debugging, we're just going to print the time remaining, and we're going to put the time remaining on the counter display. So hopefully these match up. If not, you might want to check the wiring on your 7-segment display. Finally, if the time remaining has officially hit 0, then we want to display done on our 7-segment display. If it doesn't, then obviously check to make sure that the wiring is correct. And then go down, and we should, by using the first page, last page memory saver functionality that I really do enjoy, we're going to display the following information on our OLED. And those are going to be exploration lander, liftoff aborted. We have the confirmation systems and thrusters all off, and then we're going to have the countdown abort, because that's something we're going to be getting into tomorrow. Down here below, we have the functionality that calculates the elapsed time, essentially how much time that we have been executing in the loop. And this is going to be the millis, which is what time it is right now at this point of execution, minus the countdown time where we called it earlier. So we're just counting the time between this line of code, and then we're going to count the time between this line of code. And if the elapsed time is less than the countdown milliseconds, then we're going to simply set the time remaining equal to countdown milliseconds minus the elapsed time. Otherwise, time remaining is 0. And finally, we have this functionality here for our 7-segment display. All this is going to do is it's just simply going to tell us how many minutes and seconds we have left on the counter. So if we put something like 70 seconds, then it will be able to display it as 110, or you know what I mean, minutes, seconds. So this can work with any number of seconds. Technically, if you try to do something larger than 99 seconds, you will probably not be able to display it properly using the display. But I don't know why you'd want a timer that long anyway. Next, we have the draw string down here, which simply just draws a string on our OLED, and we used this yesterday. And finally, we have the display lander. So this draws an image of our lander with triangles in various frames, essentially rectangles, at X location, Y location, relative to the upper left corner. And with that, that should be the end of day 23 code explanations. It was a long one, and tomorrow is probably going to be just as long. Just so be prepared. See you then.
Welcome to the Day 23 wiring example video. Last time, we succeeded in testing out the function and programming of our OLED graphic display. Today, we'll take another step toward getting our craft ready for launch by incorporating the display into our countdown checkout system. Using what we've learned in previous days, we'll be displaying the minutes and seconds to liftoff using the 4-digit 7-segment numerical display, while simultaneously providing system status information to the pilot on the OLED. Now, to wire up this combination of devices, we need 4 wires each for both of our displays connected to the Hero. 2 of these wires, the black ground and the red plus 5 volts, are common to the 2 displays and can be shared. Now we might choose to share these connections using a breadboard bus, as we've done several times in the past and is shown on our provided illustrative wiring diagram. Alternatively, you can find equivalent ways to wire the connections that might be easier or more convenient for your circumstances. As an example, you'll notice that here, since I've been using an extra breadboard to provide convenient connections to the OLED display, it was easiest for me to share the ground and 5 volts directly on the corresponding columns of this extra breadboard, thereby avoiding the clutter of a few extra wires. We see that the OLED is connected just as before to the Hero with the clock, that is the green wire, and the data, the blue wire, connected to pins A5 and A4 respectively. As for the 4-digit display right here, the power and ground are tapping off the same two breadboard columns as used by the OLED, while for this display, the clock and DIO wires go to the Hero output pins 5 and 4. And those numbers agree with what's specified in the hash define lines in our software sketch, if you want to check that. Now, whether you choose to wire your circuit up using power and ground buses, or perhaps using a shortcut similar to this, you'll want to try to keep in mind to set aside some blank real estate on the breadboard in anticipation of the additional components that we'll be adding to our launch system in the coming days as we build up things and get them ready for launch. For now, all we have left to do is to run our sketch for today and verify that the things we've built so far are functioning as designed. If we review the sketch, we see that we would expect the sequence to begin by initializing the countdown clock and flashing it on and off 3 times. Then we should also see an introductory graphic on the OLED screen. Next, our numerical display should enter a test countdown mode, showing the time left until liftoff. And then finally, when the countdown reaches 0, since this really is just a test with several of our vital systems not yet operational, the sequence is terminated, awaiting further instructions. So let's go ahead now and run it. I'll go over to the IDE, upload the sketch, take a few seconds for that to compile, and then we should be looking for the beginning of the countdown flash sequence and the introductory message on the OLED. So our compilation phase is almost done, and there we go. There's 1 minute and 10 seconds, and the countdown has begun. And we've got our introductory message on the OLED indicating that our countdown sequence is active and the countdown is underway. So in just a little under 1 minute, we should reach 0, and at that point the countdown will be halted as this is a test. So we'll just sit and watch this and see if everything finishes up as expected. 30 seconds left in the countdown. And in just 10 more seconds, we should reach the end. So we'll watch the OLED and see what it indicates to us. 3, 2, 1, and 0. And there we go. So our numerical display indicates that we've finished the sequence. We're done. And our OLED indicates the status of our system. We didn't actually lift off. We didn't want to. We still have to take care of these additional systems, and so the countdown was aborted. But this is all as expected. It looks like our countdown test sketch is a success, and we're ready to move on. So that looks pretty good so far. Just make sure that you understand the logic both of our software and our hardware hookups at this point, and then we'll be ready for the next day's addition to our launch system. So we'll see you then.
What an extraordinary day it's been, Explorer. We've programmed a successful countdown simulation. If that doesn't scream readiness, I don't know what does. I'm tempted to have a miniature celebration right here in this spaceship of ours. Even so, let's hold off on that for a while, shall we? We've got the most thrilling day ahead of us tomorrow. We'll be tying up all the loose ends, integrating Countdown with the rest of our hardware, and preparing to break through this planet's gravitational pull. So, rest up. Tomorrow, we're literally aiming for the stars. Sleep well, you've earned it. Light speed, Explorer, and try to be, on time.